going to talk to you about all of you guys' favorite subject. Guess what it is?
Sandwiches. Sandwiches.
Math.
Yes.
Okay, for all you guys unminded people, unmathematically stimulated people, I'm going to make the technical side really, really short. And I decided to take pity on you all, and I have pretty pictures for you guys to look at in case you're completely bored. So you can at least look interested. So, my story of math begins at the very beginning of time, whenever you'd like to argue that was. And then the stars were formed, or created, or distributed, or big bangs, whatever. And many people think they just came out randomly, which is not the case. They actually came out in a pattern that is very easy to mathematically model and represent. Likewise, the way the galaxies form, the planets, the solar systems, the atoms, everything can be mathematically modeled. So, we're going to skip all that and move a little bit further in life to the part where we actually can all relate a bit more. There are many, many more examples of how this concept can be used in space, but it would take ages to outline them and you guys would be totally bored. So I'm going to move on to a very simplistic and common approach to this mathematical concept, a broccoli. So, a broccoli is a very common object to all of us. It looks like, well, a broccoli. A green stem with a darker green mass on top. Now, what is curious about a broccoli, though, is the level of self-similarity that it entails. When I began to cut the broccoli into smaller pieces, they all exhibit a level of similarity to the whole that is remarkable, if you stop to think about it. You can cut these over and over and over again, and they will all resemble the bigger broccoli until you get down to the very, very little small fiber strands that make up the whole broccoli. So, perhaps you now have some form of curiosity towards what mathematical concept embodies this. Or because the fact that you're all taskers and not the average high school student, you probably actually already know. So, where did I go? The pattern of self-similarity in nature is known as fractals, and is, in my opinion, one of the most interesting mathematical discoveries of our current time. Now, in order to avoid the horror of TASP forming an exclusive relationship with Wikipedia, and to cultivate a sense of inclusiveness with the rest of the internet, I will define the concept of fractals from a different source, the Merriam-Webster Dictionary. So, a fractal is any of various extremely irregular curves or shapes for which any suitably chosen part is similar in shape to a given larger or smaller part when magnified or reduced to the same size. Doesn't that sound exciting? Well, this in itself seems very vague and slightly confusing, and I hope I can shed some light on what it actually means and how it's actually a mathematically relevant concept. So, fractals exist in many, many, many aspects of nature, and the self-similarity found in them has been studied for beauty from as long as man has been around to see it. A tree is a very common example of a fractal. You start with a big trunk, which then branches off into bigger branches, which then branch again and again and again and again until you get leaves, which have little veins in them that branch. So, it's nearly everywhere are trees and the patterns of lightning and the sky and the clouds and animals' coats and feathers and the rivers and the mountains and fronds of a fern and, oh, it's in us too, in our hands and feet and lungs and blood vessels. Okay, more like that. Our blood vessels display the same fractal pattern as they go bigger and smaller and smaller and smaller. So, while the term of fractal was not used until 1975, civilizations have found nature's complex geometrical patterns fascinating for centuries, such as the famous Japanese painting of waves. This is a very good example of early fractals. They have the big wave, which branches into smaller waves, which branches into smaller waves. And without that, you would lack the realistic complexity and power of the image if you just had a big C shape. So, let's see, I lost that. This is a fractal pattern, and it gives the painting the complexity that makes it powerful. Even today, fractal patterns can be found in art that seems to have no pattern whatsoever. This is one of Jackson Pollock's splatter page examples, which looks completely random to me and to you, but computers can actually find a fractal pattern to it. And this suggests that natural objects tend to fall into a fractal pattern even when you're really attempting to make them not to. So, fractals play such a huge role in the universe and our lives. Why did it take until 1975 to truly define them? Well, part of the problem is that for centuries, mathematicians lived by this rule book of geometry is straight lines and uniform curves. And they tried to define everything as in straight lines and uniform curves. So, the problem is, the only thing that's really a straight line or a uniform curve is things that man makes up. So they can never truly define, with math at least, anything in nature. So, here is the history. Before 1909, several mathematicians had begun to describe what they saw as the self-similarity pattern in nature. But their definitions were very abstract and they couldn't really figure it out. One of the most important beginnings was in 1904. Albert Koch developed a geometric definition of a very simple fractal pattern. And it's called Koch's curve. And it basically, as you can see, starts out with a straight line, an equilateral triangle stuck in the middle of it. And he said, I am going to repeat this pattern infinitely more times, and each time, every straight line, I'm going to do this. Now, this presented a very interesting conundrum to the mathematicians at the time, which believed that if you had a shape, you could measure it. And this shape you cannot measure, because every time you do it, the length changes. So, for a while, the mathematicians just scratched their head at this. They called it something called a monster, and they decided they were going to completely ignore it until they could understand it. So, that's there. Several other scientists started to follow Koch's idea, and there's many more monsters, which mainstream scientists just said, well, that's interesting. We're going to forget about them. Until Benoit Mandelbrot. And he was a man who was born in 1924 in France. And ever from an early age, he was known for his very abstract way of thinking about math. So, he had to flee from France to Poland in World War II because of his Jewish background. And both during the war and after, he studied at a variety of well-known universities and under some of the best mathematical minds of his time. And then he worked for several colleges until 1958, where he moved to America and began to work for IBM, which you all know developed the computer. And that is where fractal geometry really began to take hold. So, he had not been able to really do much with fractals until this time. Well, they weren't even known as fractals. They did not exist. Well, they existed yet. They had not been defined. Because a fractal concept is very, very difficult to do without a computer. You get to about this point, and you can't draw them anymore. So, with the new computers at IBM, Mandelbrot was able to fully embrace and work with his fractal ideas. So, he postulated that self-similarity is not just in nature. It is found in many, many other things, including he studied economics, which he actually found that much over time, if you take a humongous span of years, the graph of it will actually look quite similar to smaller spans of years. And he kind of debunked several other theories in the process. And also in informatics systems and fluid distribution, he found that fractals, or the self-similarity patterns in nature, are present. So, after all this work, in 1975 in Europe, he published Fractals, Form, Chance, and Dimension, which was published in 1977 in the US. And it was a book that was widely disregarded. Nobody really took him serious. Oh, that's cool, there's guys drawing pictures. How wonderful. So, that was kind of a flop for a long time. So, he decided, well, that was interesting, I'm just going to keep looking into it. And he started looking at Julia sets. Now, Julia sets are a fractal pattern much like these, much more complex. And they are fractal patterns described on a graph with complex numbers. But they have many issues because in certain circumstances, if he worked them out, the world would have blown up because there was issues with them. They were invariant under certain transformations and such. So, I think he kind of viewed it as a challenge. I am going to make this work. And while studying these, he developed his own fractal set, which is called the Mandelbrot set. And it's kind of a universal Julia set of all the, thank you, sets. And it looks like, oh, that was him. I'm sorry. On his second point, he looks a lot like my grandfather. There you go. The set looks like this.
Looks like him.
Now, I'm sure very many of you are wondering how a simple mathematical formula can turn into that. So, I am going to try to explain it to you, and this is where I diverge into my little technical discourse, and you guys can just look at the pretty picture if you don't care. And so he started out with a very simple formula. Oh, and you can't look at the picture, I'm sorry. Z equals Z squared plus C. Now, it is quite hard for anybody that doesn't really think about it to figure out how that turned into the humongous picture. So I'm going to find a few terms. C is a constant that remains the same through the whole thing. And Z is a complex number, starting at 1. And the equation is repeated infinitely more times, where you start with 1 and then you just go over and over and over and over and over. So, and the value of C in the end really doesn't matter. It's more the magnitude of C. So what we get is an infinitely long list of numbers for one point. And you have to make this long list of numbers for all the points. And then we get to the point of we have this humongously long list of numbers that means nothing right now. So we have to figure out how to graph them. And all of you know how to graph, but here we go. The real numbers are on the x-axis, and the complex ones are on the y. Now, the Mandelbrot set lives right about here. And anything else is kind of gone. So, once you start plotting these points that you got, you end up with something like, not that, this. A black blob. Which really looks interesting, but it lacks the main thing that people ask me about, which is color. How do you get a mathematical concept out of color? So, I somehow got my slides in the wrong order. This is how you get color. So any number, when you put it through the infinite iterations of the Mandelbrot system, will get you a graph kind of like this, where each one of these is, 1. Now, if the number stays below the value of 2, it's considered to be inside the set, and it's colored in as black, which gets you your black thing. Now the color comes in with these numbers that are not part of the set. And all these numbers are ones that go above 2. And what the color they assign is the quicker, in English terms, the quicker that this blue line gets to above 2, the different color it's assigned to it. So, yeah. And why do we need color? 1, because it looks pretty. 2, because it actually has scientific value. They use the different colors to kind of describe how fast the set sets. And it also helps you see the smaller, littler pieces of the black that you would not be able to see otherwise, because they're so small. So here comes the fun part. We're going to analyze the entire set, and here comes your reward for listening to me, all these pretty pictures. But here's kind of a small, simplistic view of the color system. Here's your axis with 0, 0, and it goes down to -2 and up to about right there. This is your black, and these are all inside the set, and your color zones, which shows you how fast it went above 2. And an interesting note is every single one of these color lines goes all the way around the shape, and it never intersects with any other color, which is kind of mind-boggling when you see the whole thing. So, now the other interesting with the Mandelbrot set is it starts with this central heart circle thing. And this heart circle thing is repeated many, infinitely more times through the whole set. Transformed, rotated, flipped, kind of smushed at times, but it's there. Many times. And let's see. The length around it is known. It's called infinity. The area is unknown. Thus. So, anything else? And now comes the pretty pictures. Here's your Mandelbrot set. Now, what makes it so cool is you can zoom into any piece of it, and it kind of shows the similarity with the rest of it. So I'm going to kind of take you in on this little tour down to really, really small. But there's never a stopping point for it. So I think we're starting with this next. See, we get that. And now if we zoom in closer on one more small part, here we go again. Yep. So can you still see we still got the heart shape with the circle. And there's another one here, and here, and here, and here, and here. The picture's kind of blurry. So here we go, zooming in again. And now you get a better picture of this whole thing. You got the same shape we started with. And this is in the big picture. Here was the big picture to begin with. This is like a point method. And here we go again. We're going to zoom in right here. Now, each one of these little squiggly things on the sides are the same Mandelbrot cardioid circle. We're going in here again. You'll be able to see it better. See, they go smaller, smaller, over and over and over and over and over. Now, this line is still a black line. It's just much harder to see. It connects it to the rest of it. And here's your little black line, which is much cooler on the internet screen. But in these, you're going to have your little black, same Mandelbrot set. Here we go again. It kind of looks like a sun exploding. And here it gets cool. So, this is your black line that connects it. In the middle, you've got your basic set. It's actually two of them squashed together. And it comes out like this. Now, you have to remember, all these points are the points outside the total set. They're the points that have been receding away from the screen. And thus you get the color. And would you ever think that was in there from the original picture? You get your whole shell-like shapes, and all these little dots are, guess what? Your same Mandelbrot shape. And I think there's two more. Here you go again. Inside and there and there and there. And you can kind of see the different coloring bands around the thing. And here, oh, no. So you can kind of see this has more of the same Mandelbrot sets. And that one's the final picture. Well, it's not the final picture. You can keep going. Oh, no. So, there we go. So you see that it's a really cool, aesthetically pleasing thing. What's the point? Why is this important? Well, one, it's made animation possible. Before, when mathematicians were still viewing that things had to be in circles and squares, you had like Mario with him running around in squares. Now, you can have such things as the animation of planes flying over mountains, the animation of, oh, I think I have this. Oh, never mind. Well, the animation of Star Wars, that was made because of fractals. Many, many, many hours of fractals. And dinosaur skins in Jurassic Park were also fractals. So that's, I guess, important to everybody else. But to the scientific world, there are also many, many uses. And a short list, there is weather forecasting, mirrors, plant creation, population biology, characterizing and distinguishing metals, pollution mapping, astronomy, economics, anatomy, chemical reactions, molecules, Big Bang Theory, fashion design, and many others. Okay, one of my favorite studies out of this whole thing, that's a picture, is a team of scientists went down to Costa Rica in the rainforest, and they actually cut down a balsa tree, which you would not think a scientist were doing. But they cut down this tree, and they measured the whole thing from all the big trunks to all the small branches, all the little leaves. And with that, they were actually able to map the whole of the rainforest using just one tree, with the big trunks representing the big trees, and the smaller ones coming down to the twigs being bushes. And with this, which sounds completely crazy, but it kind of, to me, represents the whole interconnectedness of this fractal nature geometry through everything that to us just looks like a tree. And they're using this technology to map actually how much carbon dioxide the rainforest can take in and take out over time. So I kind of compressed that whole section fast. And here are some semi-random facts about it that I just thought were interesting. The Mandelbrot set can calculate pi, although pretty ineffectively. It also has uses in music. You can take as little as 1.6% of a composer like Bach or Mozart and still find the common essence of them in it, which I think is pretty cool. Without computers, the set would be completely invisible. And there are many, many, many awesome programs on the internet that you can zoom in and look at it all if you want. So that was my speech on fractals.